Welcome to everyone for this plenary lecture by Daniela De Angelis, who is Deputy Director of the MRC Biostatistics University. I was going to say here in Cambridge, because we're all supposed to be in Cambridge. And just welcome Daniela and give her the floor.
Okay, thank you very much. I don't know how many of you there are out there. I should start by apologizing. This has been put together at the very last minute, so I hope you understand. It's not been rehearsed, so I'm not quite sure exactly how long it's going to last for. But when Dennis invited me to participate, I thought maybe silly that I would be able to put together something given the 2 weeks notice that he'd given me, but at the end it didn't work out so well. But anyway, I have a number of slides, and you'll see they degrade over time, the quality degrades, so I do apologize for that. Okay, so this is an opportunity for me to give you some sort of feedback, or to inform you about the latest developments on the COVID pandemic in England. I am one of the members of the SPI-M group. It's a subgroup of the emergency group of the government, the so-called SAGE, and we've been working very hard in the last, I don't remember how long now, but throughout February, March and April, so it's around 3 months, to provide evidence for decision making. It's been an interesting experience. The idea here is to give you some sort of flavor of the type of work that we've been doing. Typically, this work is not totally clean and finished as one might like, but the situation is so fastly moving that, as Graham Medley says, it's better something now less perfect than something perfect if it comes too late. So we've been doing a lot of work to trying to address the problems that were coming up and to use the data that accumulate with all these problems. And I think this is a little bit of a short history of the last few months. So I'll start. So let me first of all give you a little bit of background. The background starts roughly 10 years ago with the 2009 pandemic, when I was involved in the H1N1 together with what was called the Health Protection Agency, and now it's called Public Health in England. They did have some limited capacity to do any work for that pandemic in terms of monitoring the epidemic. It was evolving, and so a collaboration with the MRC Biostatistics Unit was developed to develop methods or model for real-time pandemic monitoring. So the original model, which we published then in 2011 in PNAS, was also this type. Let me just describe it very briefly. It was a deterministic, in fact, it's EEIR model, which would govern the transmission of the disease. It was an age structured. Then, of course, this process is not observed. What we see is a number of data streams, which would then inform the estimation of the underlying parameters, reconstruct the epidemic process, and if necessary, predict, although at that point we were not interested in predicting. Okay, so the first component was a deterministic model for transmission. Then we had a quite complicated and convoluted model for the disease model and for the observational model. And we had a number of data streams which was feeding into the estimation, which was in a in a Bayesian framework. So these blue boxes represent the data streams that we had. They were all incomplete, they were all biased, and so we had to use additional data sets to make use of what we saw. And then combining prior distribution on the parameters of interest, particularly obviously of this lambda AT, together with the likelihood, we could derive posterior distribution for the parameters and then estimate the epidemic process. And just to give you a little bit of a flavor, no, I'm not going to go in any details. We had data on case confirmed cases at the very beginning of the epidemic. We had information on GP consultations, which obviously had an element of background, so they were a very noisy signal. And then we had information over time on zero prevalence in the population, so a series of snapshots. So this was the setup of the model in 2011. Now, the question, okay, this says exactly what I've just said. The only thing that I didn't say is this was a Bayesian model, and the posterior distribution was obtained through simulation, Markov chain Monte Carlo. So this is the list of the data I've just mentioned. So we use this model in the paper to estimate the H1N1 pandemic in different regions. Here in London, we had an initial R0 of 1.72, a total number of infection of 1,033,000, 27% of which were symptomatic. So this is basically history. We did the same thing in different regions, although we were modeling regional epidemic independent of one another at that point. So, however, this was a retrospective, this work was as a retrospective epidemic reconstruction. It was not online inference. The regions were analyzed in isolation, and there was a potential for new data streams to come along for a future epidemic. So we needed to develop the model to enable online inference, to maybe model the regions simultaneously, so a meta-population model, and to use additional data sets or data streams, which will probably will have increase the computational time, and then at the same time pose other problems because data are never really easy to use and interpret. So we did apply in 2012 for an IHR UK pandemic influenza research portfolio. This was a series of some funding that was made available to people to prepare for an eventual pandemic. So to do developmental work in such a way that this developmental work will be ready as a new emerging pandemic, is a new pandemic was emerging in the future. So there was an initial phase, a pre-pandemic. So we did exactly what I've just said. We did spatial modeling, incorporation of data from different surveillance schemes. We improve the computational aspect to make it real time. So we did quite a lot of developmental work. And of course, within the grant, there was a second phase, in pandemic phase, where all these projects, ours was one of them, would be activated and be ready in the event of a sudden pandemic. And for us, this part here was to provide modeling and software support to Public Health England in the provision of relevant estimation forecast. So before January 2020, We had published papers developing this tool. We had a software on Git. We'd done all sorts of other things, and we thought we were ready. At least we even used this model for seasonal influenza, so we kind of tested it. And so in principle, we were ready. But were we really ready? And this is, I think, the little story I'm going to tell you about this. Tell you the story of the adaptation of this model to a different type of epidemic, whose characteristics are still not clear. And so, in a way, about the naivety with which we embark into COVID, saying we've got the tools, we can do what is needed. I'll give you an idea of the current climate and our participation in SPIAM group. I'll tell you a little bit about this model in some detail and how it's been adapting to the new epidemic, and how it was being used to generate evidence for decision making. Before the lockdown, it was used as a simulator to provide scenarios of possible pandemic profiles, and after the lockdown, it was used in the way it was meant to be used, as an inferential and prediction tool to provide nowcast and forecast of key epidemiological quantities. And then I'll tell you about all the tweaks, interesting tweaks, that we had to make as data accumulated to make full use of this model. Then I'll probably, if I have time, I haven't timed this, so I don't know how long I have. I'll give you some ideas of the current challenges. Okay, let me just tell you about this Scientific Pandemic Influenza Advisory Committee, SPIAM. It was constituted during the H1N1 pandemic in 2009. It is to support SAGE, which is the body that makes decisions in an emergency situation, and these particular pandemics are emergency situations. So basically, SPIAM provides expertise on the quantitative expertise on the analysis of data and the construction of and the estimation and of transmission dynamics. So anything that has to do with transmission modeling is in there. SPIAM was maintained after 2009 to ensure preparedness in the event of a pandemic. We will be meeting for the last 10 years, at least twice a year, if not more. And more recently, I think the last meeting before this pandemic was at the end of November. The remit of the SPIAM was extended to just influenza, because the idea is to prepare for a pandemic, influenza pandemic, to extend this remit to more general emerging epidemic. And the members of the SPIAM drawn from all sorts of universities. I haven't made the list here, but you can imagine the usual suspects: Imperial College, the London School of Hygiene, Warwick University, Lancaster, Exeter, Manchester, Edinburgh. So there is a lot of expertise to be used in this, and then lots of different people were brought in as needed throughout, and they are still brought in as needed, because the tasks they are given coming really fast. They have a very short very short notice, and for most of the period we've been working with a deadline of 48 hours. So you need lots of resources to be able to cope with this type of demand. Okay, so let me sort of generically explain a little bit about that model that I've described initially. and this is an age stratified deterministic models, which has got two substates for the latent and infection periods. This is the continuous time formulation. It's quite a simple model. It's not very complicated. The force of infection is in particular a function of this matrix, which is the metric contact matrix, which changes over time, and in this situation is actually a very important concept. So the new infections, this is okay. The new infections are generating in this way. STA is the number susceptible at a particular time on a particular age group, and P lambda T is the probability of infection given by this expression here. This is a Reid-Frost formulation. MTAB is the B entry in the age group time vary mixing matrix. R0 is R star is the scaling factor. R0 is the reproduction number, and we use the Wearing formulation, so we express it in terms of the growth, the exponential growth rate. Yeah, and here DL and DI are the times, the parameters, and so they indicate the time spent in the latent and infectious state. So this is the typical metrics that you can imagine from Polymont. So the initial time 0 is this, which describes the daily average content that each individual of a particular age strata has with another individual in a different age group. This was the initial matrix, but then of course after the lockdown the matrix of content changed, and we were able to derive the other matrices by using information from Google Mobility and time use surveys. Okay, so this is basically the structure of the model, and with this type of model you can do different things. And there was an initial phase where the model was used as a simulator just to create possible scenarios. This was at the very beginning of February, when obviously it was clear that something is happening in China. Maybe there were already some episodes in Europe. Maybe some cases have been confirmed. You may imagine, you may recall the famous cluster in Germany, and there were already initial people confirmed in the UK. But although there were imported infection, and I was clear, there was a Chinese couple, mother and son in York, and then they were announced to be positive at the end of January. So by the beginning of February, there was already a lot of movement, a lot of activation in terms of sort of political and scientific, in the political and scientific world. And in particular, the famous SPI-M met on the 27th of January, and they gave one of the initial tasks. So one of the tasks that we were given using this model is to generate possible scenario, or what an epidemic in this country would look like if it had the same characteristics as China. So that's what we did. And if you remember the expression here of R0, we basically used data coming from China, not really data, estimates of import of the serial interval and I think it was the serial interval, the incubation time, and basically the relevant parameters which were already being estimated by a number of groups in China to produce possible epidemic. So we took the interval, so the Selinger estimate and the interval, as if there were sort of a range from which to estimate to sample the various parameters DI, DL, and the growth curve, and we're generating possible R's. Then, having generated possible R's, we generated all the infections that resulted. And I don't know how well you can see this this plot here, but this is basically an example of the resulting epidemics in a situation where I think we started with 100 infected individuals, yeah, 100 individuals. So we're generating this epidemic. You can see, perhaps you can, or you cannot see, but the dark color correspond to the very high R0, and then the red ones to a smaller R0, and you can see that the level of infections, which is difficult to read here, was very high, and the epidemic would be extinguished very quickly if the R was very high. Whereas for an epidemic characterized by an R which was lower, there was a longer duration and a smaller peak. See if I remember the level of infection, but you're talking about sort of millions a day. So the question that was asked was the magnitude, and this gives you an idea depending on the R, the peak. This is a distribution of the peak, and the duration. So this was the kind of information that they wanted. What kind of epidemic are we going to expect if it has the same characteristics? So with us, like everyone else, did lots of simulation to try to understand regional profiles, age profiles, to try to understand whether, for instance, there would be a synchrony between different regions, which obviously depended on the type of seeding. So there was quite a lot of work directing in this way to try to understand what the potential pandemic would look like. And this was at a very initial part of February, and in time and over time in those early days, there was a lot of work to try to understand whether there was established transmission anywhere. In the meantime, this is a data set called the FF100, so the first few hundred. This is a study that was initially set up in 2009, and then, of course, activated, reproduced again now by Public Health England, and the idea is that of the initial confirmed individuals identified, which initially were all mainly people who had come back from China, they would track the possible contents, and they would test them, and so this data set, so this study was to identify all the contents. They would follow up all the contents and understand whether they would develop symptoms, and then so on and so forth. So there were, you can see here that throughout February and the beginning of March, This was the number of confirmed individuals, all of them. So there were not very many. And you can see that there were mainly sort of people returning from other countries. So not important, the number of not imported was quite small, and it seemed to be almost going down, but it wasn't really going down. We discovered at that point that there was a reporting delay, and this is the same curve that I showed earlier, and this is the numbers adjusted for reporting delay. I mean, admittedly, we didn't put I didn't have a picture where there was a confidence interval here, but you wouldn't want to do that. So actually, the scale was quite different. Once the reporting delay had been accounted for, the curve in the first few hundred was showing some trend. Okay, so much so that we could even fit an exponential curve. And this was the very early stages where the testing and the tracing and testing was quite homogeneous, so it wasn't changing over time. There was a policy to do that. So what you would see was actually the result of a sort of consistent policy on testing. And it was evidence of this type, work by others in early March, predicting that the NHS would be overwhelmed by the number of resulting hospitalization and admission to ICU, and that triggered the lockdown. So this is the kind of work that we were doing using the model initially, and then we were doing also data analysis to try to understand whether there was any initial sign of established transmission in this country. So we arrived at the lockdown. Now, after the lockdown, our model was used for, fully for its purpose. So nowcasting, so reconstruction of the epidemic, estimation of the parameters, and understanding the level of infection at the current time. And then it was used to forecast relevant data. Now, what kind of data are we talking about? We're talking about time series of confirmed cases, which was reliable before there were changes in testing strategy, and I think the testing strategies did change around about mid-March. Then we had time series of deaths of people who had been confirmed as being positive COVID. Then much later on, you might have heard an awful lot about this, serological data on immunity or antibodies, and there are at the moment lots of studies, but we decided to use the data on the blood transfusion. And all data were stratified by age group and by NHS regions. Now, it's not quite the rich data sets or data streams or collection data stream that we had envisaged and we had planned for, perhaps even done, not perhaps, and done the developmental work for, but that's what was available at that time. At that time, it is available now, actually. So I've kind of reconstructing, I hope it's not too boring for you, some sort of little timeline. So important points where the data, the availability of the data, or the problems in the data required some sort of different, evolution of the model. Initially, the data were very limited, and so we couldn't do any full. The model wouldn't make sense to exploit all the various flexible aspects of the model by age, for instance, by region. So we started with a much reduced model, which used the data initially available, and then as data were coming through or becoming richer and accumulating, we could analyze things in much more detail and adopt a model which was becoming more realistic over time. So, for instance, in March, we said the lockdown was 23rd, and I think around those days we started to use our model as an estimation tool, as an inferential tool. So we used the data, and but we couldn't understand. No, we couldn't estimate the effect of the lockdown. So I'll show you what we did instead. And we were looking just at London, outside London again, because the data were limited and it wouldn't allow any particular stratification by region. By the 29th, by the end of March, we had decided that that we would use only the data, and we dropped the line listing. Let me just go back for a second to this. I said there were confirmed cases, there were dense, and the serological samples. These are the data that we used. In reality, there were many more streams which we did not consider, and these were the hospitalization and the admission to ICU, which they came more in terms of the number of people in hospital and the number of people in ICU, so cross-sectional data rather than incidence data. There was a way of deriving some sort of measure of the incident, but it wasn't so neat. Also, those data, according to us, could suffer from changes in policy or admission to hospital, and so we were not quite clear whether we could actually account for that, and so trends could have been masked by changing policies, which could have been different. And I think there is a little bit of evidence that those changes were different in different regions. So we decided not to use the hospitalization data, not to use the ICU data, and so we decided to just use the data. Neat and strong signal, but of course a little bit delayed compared to the other data sets. Anyway, so this was March. Come to April, we started to accrue more data, so we could actually develop a regional model. We could start estimating the lockdown effect. Remember that our model is a Bayesian model, so the lockdown effect was through a particular type of parameter, which initially had a very strong prior, because there was not very much information on it. So we progressively able to relax the prior and let the data speak. And then on the 13th, we started to look at the model, age-specific model, given that again data were accumulating, and we could use the age stratifying data. Also, the content matrix was allowed to change over time from the initial polymod. As I said, we were acquiring slowly data on movement, and so we could formulate a new matrix, which then also started to account for some of the effect in transmission, in change in transmission. On the 16th, we'd also elaborated a little bit about the time to death, because obviously what we were using it was any information about IFR, so the infection mortality, fatality ratio, and it's here, and the time, the distribution of the time from symptom onset to death. This kind of information on the severity were initially taken from the Chinese, but they soon by mid-April they revealed themselves not appropriate, and with the result that we were getting really strange results from the estimation, like the whole population by this time must have been infected. So there was something not quite right. All of this seems to be automatic, but it's not if you think that these kind of results were provided every 48 hours and you only had really a short time to assess whether they made sense or not. So as we were progressing, we were changing, tweaking the model to be able to reproduce the data, and some of the data were suggesting that some of the initial assumptions we were making were not appropriate, and this was the case here. May, which is last week, but it seems already a long time ago, but we started to use the data on the serological data from the blood donation from blood donors. So we had some information which was age and region specific on the proportion of the population who had antibodies. And then again last week we started to see whether we could estimate the effect of a relaxation. Let me go into some details. The complicated model that you saw at the very beginning with lots of data sets actually is much simpler now. So this indicates that the incidence and the parameters are informed by the initial set of the initial data on the confirmed cases. It didn't last very long, as I just told you, and then from on the deaths, the time series of deaths, and therefore the probability of dying, and the time from onset or from infection. You can reconstruct the time from infection to death, and then later on, more recently, using the seroprevalence data, which gives some information on the proportion still susceptible in the population. Now, one very interesting problem is the data. And this figure shows it quite well if you can see it. This is the count of deaths by date of death at the end of March. By region. In this case, at this time, we were only looking at London, outside London. But you can see what the problem is: the serious reporting delay that we were experiencing. So not only the data, the deaths are a delayed signal, but we also needed either to estimate the reporting delay and adjust again this also by reporting delay, which meant obviously we had to sort of scale up the last few days at least, or ignore the information in the last few days. Now this is another seminar to give the problems about the adjustment of reporting delay, because the reporting was very extremely haphazard and not very easy to estimate, and so any existing method was really not appropriate. It was giving an awful lot of variability, and it was very dependent on the reporting pattern, which was changing basically by the day. So we had to ignore as a safe option here. We had to ignore even few more days to avoid to get rid of the bias due to the reporting delay. Okay, so these are the data that we initially used in the initial 23rd or 23rd of March that I've just mentioned at the beginning. So we had this line listing with the confirmed cases. These were affected by a reporting delay as well. You can see these are the data. The blue are the data to the 23rd, and in the red the data to the 20th, and you can see that the case count, for instance, we only use them up to a point. This because they were affected by reporting delay, and the same thing here, data comparison. Okay, so what did we do? We fitted the model using the two streams. We estimated the parameters, and we're trying to reconstruct the underlying terms. Of course, there was a big uncertainty in the impact of the lockdown. So what we did, we generated high, medium, and low impact scenario to extend the estimation of the epidemic curve beyond the lockdown. I just wanted to say that at this stage, these are the curves corresponding to the medium, to the high, low, and medium effect. I think the low effect was 24% reduction in transmission. The high was 64, and in the mid was 48. You might wonder where we got these numbers from, but they were informed information by some data on contact tracing, content on content metrics, or contents between the metrics or contents literature. So this was a reconstruction of the number of new infections. Obviously, the impact of the value of the impact of the lockdown would make an enormous difference. If the impact had been low, then we would have observed, at least that's what we're reconstructing and predicting, a very high peak around about, we're talking about 3 million here. With a very high, we would have possibly sort of diminished the number of infections, but still, the uncertainty was quite big, up to a number. These are days, so up to 1 million, and in the mean was something between, suggesting a peak, but with again very, very big uncertainty on the number of daily infections. And the pattern was different, obviously, in London and outside London. But at this point, this was just driven by very, very initial data, by information, by assumptions on the possible lockdown, which we didn't have enough data to estimate, and so was just giving a very clear impression that the data were not really saying very much about the current and perhaps short-term evolution of the epidemic. Anyway, just let me go to the next step, to enter the end of March, when we started to have a little bit more information about the change, the lockdown effect. The data were accumulating, so we could put in extra parameters, which we call M1 here, to which initially there was a tight prior, because obviously the data were not enough to be able to estimate it, but this would represent the effect on the probability of infection of the lockdown. You can see that the tight prior that we were using initially was centered around 40%, and then later on we will start using something which is much more relaxed and let the data speak. So this was the way we introduced the effect of the lockdown. Of course, this M1 it was kept the same only at the level of one parameter until the second, the lifting of the lockdown the week before last. And then the idea would be to be able to try to identify whether this type of parameter changes over time. We'll see. Okay, so again, this is progressing our estimation and our prediction. At the moment, I'm just concentrating on the nowcasting, so understanding where the level of infection is. In the most small window here, you can see the trends in the number of deaths. I'm not sure that you can read the region, but of course there was an increase, and the increase was different in different regions. And I think the yellow one here is actually London. So the number of deaths were quite steeply increasing in London. In other regions, I think this is the Midlands, and in other regions the rate of increase was much slower. So there was an heterogeneity. We started to be able to identify this heterogeneity when we started using a regional specific model. And you can see that this is, for instance, reconstructing epidemic in London with a peak roundabout, so the lockdown, and the effect of the lockdown was that of suppressing the infection, but the uncertainty was still very big. These are daily new infections. There was heterogeneous, as I said. For instance, Northeast and the Yorkshire, the picture was quite different. The level before the lockdown was the level of infection before the lockdown was estimated to be much lower. Therefore, the effect was smaller, and there was the possibility of having lots of infections afterwards. What's interesting is that the R0 was being estimated as between 2.4 and 3.5 in different regions, and the M1 parameters was of the order of 0.35. So this indicating that the effect of the lockdown, although was quite uncertain, could be estimated. But I think at this point we still had the strong prior. Okay, so now we started to acquire more and more information on patterns of content between age groups, and from the original polymod, we could derive new matrices using data from mobility and using data on the time spent in different activities. It again is a little bit of a tricky calculation to explain how it was done, but we could trace, we could adopt different matrices over time, and I think this were changing every week, and therefore they were absorbing or explaining some of the transmission. So perhaps from this point on, the value of this M parameter wasn't so clear. It wasn't the one that was absorbing all the difference, and it could be interpreted now more like a contribution to the change in transmission beyond the change in content, which could be formalized and expressed in terms of these matrices. So a kind of random effect, if you like, although it wasn't a random event, but it would account for all the remaining unaccounted variation in transmission. So we had number of matrices. This is, for instance, the one that we were using the week of the 30th, and then at the beginning of April, and then here I think is in May, and we have these matrices every week. Okay. Now, as we're, you know, we at the beginning of April, we had a trend, an increasing trend in deaths, and slowly, you know, we started to observe declining trends, particularly in London, where the other regions maybe were still having sort of constant number of deaths. This was the 26th of April. You can see that we were even changing the way we're visualizing our results. Now we had an RT, which was obviously changed through the metrics and through the to the M factor. We were estimating something between 0.5 and 0.75. Remember that before the lockdown, we were talking about an R0 of 2.4, maybe reaching 3 in some of the regions. We were estimating an infection fatality ratio of 15% for those over 75, and then differential in different age groups. This is where we were fully using the data by age or the age structure. So again, usual heterogeneity. London was the one that seemed to have been experiencing a much earlier epidemic, and other places like the northeastern Yorkshire were still at this stage having over the 10,000 infection per day, and the pattern was different. The pattern of infection in the past was different. Now we come to our to much closer date. This was the 10th of May, and this is what the deaths looked like at this stage. You might have heard all the media storm that we were subject to last week. The epidemic seems to be sort of almost fainting in London, whereas in other areas again is still ongoing. We were estimating very low RT in London, and 24 daily infection. We can talk about that. The RT was between 0.64 and 0.8 elsewhere. Variable in different regions, but definitely lower than 1. So I mean, the alpha is still high in those over 75, and basically, this introduced for us, it confirmed for us the heterogeneity in different regions, which perhaps is due to a number of factors, maybe the level of infection before the lockdown, but at the same time the different social structure maybe and comorbidities that characterize individuals in different regions. So that's where we are now. This is just to give you an idea, because apart from reconstructing the epidemic, we were also estimating, forecasting the number of deaths, and seems to be that we've been quite successful forecasting the mortality due to COVID. Now, our work continues. I hope I've been able to give you some sort of flavor of the things that have been going on, how we progress our model, what the different components have been added over time, and where we are now. We are in a situation where the restriction being relaxed, and now we have to identify whether this has led to any resurgence in the number of infections, which is a very, very difficult mission. So the current challenges now is, I mean, the main one is the ability to track this time varying M, and whether this the data actually are informative enough to be able to say anything about the current transmission, because remember that the lifting or the reinstitution of restriction, social distance or whatever, it depends on the scientist. That's what they say, but the science is limiting. Our tools, individual, are not enough to be able to perhaps to identify swift changes in transmission. We could be using additional data. We have already incorporated serological data in our model, and this is being shown to be very consistent with the estimates that we were obtaining. So it hasn't led to a big change, and you might have seen the results of these serological surveys, which indicate that quite a proportion of young people have been infected, for instance, and so which then poses the question about age-dependent susceptibility and transmissibility, which is not at all understood. Now we have a measure of the prevalence rather than the zero prevalence, so the current level of infection from the ONS study, but this is still, the information is still very uncertain, but we are thinking that these are additional information that we couldn't, this is part of the additional information we couldn't introduce in our model, but whether we'll be able to swiftly, given the delayed nature of the deaths data, we'll be able to swiftly identify any change is perhaps doubtful, and our work, like the work of others, will need to be accompanied by other tools, and not just rely on the models. I put ... because there are so many questions that we don't even know how to formulate. I just finish with the acknowledgement. Public Health England, who has been obviously collaborators in that, through Paul, Edwin, and the PHE modeling cell, and the MRC Biostatistics Union. Paul has a double affiliation, and Joshua Blake, who is a first year PhD student, starting with me and Paul in October, and has been sort of making a very interesting experience in his first 6 months of a PhD student. Anne Presan is another colleague who's involved in the estimation of the severity of COVID-19. So I hope I haven't bored you too much. I hope I've given you a flavor of the challenges. Our work, we are only one of the possible groups in working in SPI-M. There are lots of others, and that's it. I don't know whether you have questions. Thank you.
Well, thank you very much.
I'm sorry, I didn't realize how time was passing by so quickly. Anyway.
Arnold, can we unshare the screen possibly? I had just one question about sort of spatial structure. I'm not sure whether that's at the did you just the main thing you seem to have was be considering different regions separately. Was that the only sort of level of spatial structure, or did you look at more local structure?
It wasn't. I didn't say that, but initially we were fitting the data by region on individual regions, but then some of the parameters would be common to all regions, so we were fitting the region simultaneously, and some of the parameters were considered common, so there was a hierarchical model which we use to model those parameters. Common, different, but from a common distribution. No, they were fitting simultaneously.
Okay, Ara Longini has a question. Arnold, are you allowed to?
Now, can you hear me now?
Yes, yeah, I can hear you.
I don't see much, but that's okay. Very nice for that presentation. I'm wondering, why you use a compartmental model, differential equations model, rather than an agent-based model, especially for evaluating the effect of the lockdown and then lifting it. Having a single M that multiplies the transmission matrix seems, not very good. With an agent-based model, you can, model households and quarantines and contact tracing and all these things. And I'm a little, I wonder if you can really deal with the effects of, say, lifting the lockdown in such a simple model.
Okay. First of all, I said that, what was done in 48 hours was what could be done in 48 hours. So in the days where we didn't have a task, we could think a little bit about extending the model. In reality, we are we're modeling that thing as a process. So it's not just a value that a stepwise value, so there is more to it than that. The agent-based model, the big simulation model is the simulation model that people in Imperial College use. I'm not that keen on those models. I find that it's very difficult to do inference in those models, and they're very much dependent on what you put in the model in the first place. So I totally agree, and maybe you didn't say that, but I would put here as a caveat. I agree that perhaps a deterministic model is not quite as flexible as we would like. So I would like to be able to inject some stochasticity in this model, but I don't think I would leave them in field. I wouldn't go onto the agent-based models, because I'm not quite sure how a principal inference can be done. I still need to be convinced about that.
Okay, I think with the MCMC methods and other Bayesian methods, you can fit these models quite nicely to data. But I agree there's a lot more complexity with agent-based models.
Very. In this situation, they will be ideal, and they are ideal. But the things I've seen, which is mainly is mainly scenarios.
Yeah.
But what about Martina Morris is going to tell me how to do it now. It'd be lovely, but I find it difficult to believe how we go about it. But I'm prepared to be convinced and to learn from someone how to do it. Go.
Well, Martina and Valerie had questions, but perhaps we'd better have Martina first, as she's been spotted.
I'm hardly going to tell you how to do it. But what I was going to suggest was there's maybe a middle ground here. So I'd like to echo Ira's point, obviously. I am coming in from that perspective, but primarily because the questions that we need to answer moving forward, I think require a little bit more than just a single contact reduction value, right? So the key questions I think are, where would we get the biggest bang for the buck by really focusing our intervention effort? So closing schools, reducing workplace stuff, large mass social gatherings. Those are actually real questions that people need answers to at this point. So having a single age structured matrix doesn't answer that. But then as soon as I thought about that, I realized, you know, in the Polymod data, they actually break down where that age structuring is coming from. Is it possible for you to bring that into, to introduce that heterogeneity into the framework you're using?
Yeah, so this is all hidden behind these matrices that I've presented. I didn't go into any details, but basically not only you can do that, you can break the, I think you can look at the places, and you can look at schools, you can look at
workplace. Yeah.
Yes, you can do that. And this is exactly what we're doing. It's, I should have given it just a seminar on that, but this is exactly what we're doing. We're looking not just at the original and doing.
But the aggregate, yeah.
Yeah. And so we're looking at using the polymod in specifying that way, and using the mobility, which gives us some information about the location of people and how this grouping changes over time. And then we are also looking at the time spent in different activity. So it's still a bit, it could be made more flexible, I think, but basically the change in behavior is not just through these M values. In fact, the more the behavior is more and more explained by the changing metrics over time. Okay, so the M is just an additional bit.
Yeah, I think it's still a compartmental model, so you're still just multiplying factors times matrices. Yeah, no matter how you slice it, it's not going to capture the, you know, say the effect of closing a school, for example. Yeah, they give you some proportional representation.
Yeah.
I really think it's a slippery slope to start breaking these matrices up in this way.
Yeah.
Yeah.
Yes, we are.
Valerie, did you have a?
Oh, a very little one. So could I just say first how much I enjoyed your talk, Danny? It was great. So thank you very much indeed for your efforts in doing it at even 2 weeks' notice, given all the other things that you're doing at the moment.
I put it together this afternoon, so.
Well, there you are then. So this is just, I was just curious, really. As you may know, we had a talk from Neil Ferguson a couple of days ago. And one of the things I think I remember from there was a current estimate of the reproduction number, or the range, going up, you know, the idea that it's been increasing very recently, and was now the upper limit of his range was 0.95. Now your calculations were based on data to May 10. And so I wondered if you knew what the changes were based on your model, the sort of direction of travel, really.
model is he talking about? He's talking about the...
Well, that I can't remember, of course. I just, you know, it was just some, I didn't take notes. I mean, so exactly what he used for that calculation, I don't know. So I'm really just asking if you could add another week's data, which you might have done by now, how much has it changed?
Okay, so I have to say these matrices that we track every week are already showing a change. So the number, the thing which I summarize in a very simplistic way there of the number of the average number of the number of contents daily actually is changing over time. So that is going to already tell us something. The problem is that the deaths are delayed.
Sure, sure.
So if you think about it, it takes roughly 2 weeks on average to die. So I mean, it's a neat, a solid signal, but is a signal which is delayed, if you see what I mean. So we have problem with that, and we thought that perhaps using the zero prevalence would help. But even the zero prevalence, it doesn't really particularly help because it refers to, it takes 2 or 3 weeks to develop antibodies. So again, it's retrospective. It sort of informs the past. So we will, and I think we have.
I mean, your calculations on the ones that you showed us the results for on May the 10th, they of course were also retrospective and looking back.
No, even the ones that we ran two days ago, they are a little bit of resurgence. But what does that mean? What is the value of what? Is the value now? Is the value 2 weeks ago? This is a long discussion that we're having as PIM, because obviously different people use different data sets, different delays, therefore, and it's not quite clear exactly what everyone is estimating. Neil is estimating that through they use two types of model, the agent-based model, where you know everything about everyone. And then the other one, I think, is a complementary stochastic model. And for them, the uncertainty in the estimation of the RT is so big that really definitely spans one, but so big that I'm not quite sure how can say that there is a change over time. I'm not sure. It's a problematic thing. Between you and I, maybe it wasn't the best choice of metric. It was something that intuitively could be appealing the government because it was a number, but the interpretation is very delicate. So maybe that, together with other measures, the other indicators like the current prevalence, or other measures of movement and the testing and the tracking, the testing individuals, and the results of that put together should be used as a kind of composite indicator or measure of the resurgence or not. It's difficult. I mean, we're not playing with models, and we're not. It's a difficult situation. I'm sorry.
Sure. No, I appreciate that. But it's good to hear you expand it. Thank you.
Martina again.
Is there no one else? I put my hand up in case there's no one else, but
there is no one else at the moment.
Okay, well, good. Then I will jump in. So I just want to thank you for bringing up that, focusing on R. I mean, it's such a gorgeous, simple summary of this incredibly complex process. We all get fascinated by it, but it is slightly problematic when you hold it up as the one thing that government should be looking at. And the other thing that I think we fail to adequately explain is that when you're close to the threshold, which is where we are, the stochastic variability becomes very important, right? And so it's exactly there that we have the most uncertainty about what's going to happen next, and we could bounce around for some significant period of time there.
I totally agree with you. Yeah, you could have said better than that. Yeah, I really don't know who advised that, frankly. I don't know.
I suspect it may have been something like, it was one of the first things that we as modelers wanted to estimate. And when people started asking us, you know, what should we be looking at? This was what came out. This is what we would want to know as modelers, right? It's kind of the single summary metric. And you can, the beautiful thing is you can estimate it in all of these different ways, right? So it seemed as though there was a grounding there of it in empirical data that would also allow us to get some view into this big invisible epidemic that was unfolding around us.
I suppose if you were able to rely on a very consistent surveillance, yeah, which then over time really meaningfully represents what's happening in the population. I mean, some of those.
That's the classic assume you have a can opener, right?
Yes, exactly. So, so some of those countries that have adopted testing, tracing, and testing in a very organized, in a very consistent way, would have had data which might have been lending themselves better than was happening here, to be able to derive some estimates of R. But here we just look at data on hospitalizations, data on deaths. I really don't know.
So one last follow-up then. What would you suggest if we could put R back in the closet, which I'm not sure we can, what would you suggest that we put in its place as?
I don't think you want to put it in the closet. No, I think you want to try and see whether you can try and estimate it, okay? And different groups are coming up with slightly different things, which we don't understand whether depends on the data they use or the method they use or the model they use, the assumptions. I mean, there are lots of things, but it needs to be looked at along with other measures I was saying before. These are all imperfect measures of everything because the data are not rich enough to be able to give a strong signal of what's going on. If the ONS, for instance, were bigger, the ONS study, maybe a more clear signal could come from that. Let's see what happens in the next few weeks. The mobile apps and all of that to understand the mixing, social mixing, and to guide the testing and the isolation. It is biased because obviously it depends on who downloads those apps, how the apps are utilized. I mean, all these measures have got problems. So the idea is that there's a moment of uncertainty. We've got different things of limited value that in themselves can tell you something, but on their own cannot. So I don't know. We should look at different types of indicators. I mean, the fact that people start going to a hospital, I mean, obviously is a measure of the severity. Something's going on, okay? But it could be at the same time a measure of the fact that now there are places, so there is no overwhelming. So how do you distinguish between the true signal due to the epidemic and the confounding, which depends on other types of consideration and policies? It's very difficult. But if you do have a suggestion, please come forward, because obviously everyone is now is just thinking of how to go about it. For instance, creating surveys in particular groups of the population. Okay, we know that there is a hospital epidemic, so that is pretty, obvious. We know that there is an epidemic in care homes and institutions. Okay, let's survey that. But what about the community? What about the community? Who is behaving in such a way that can induce a second wave or can induce resurgence? I'm not sure that we've understood the different groups in the population that are actually driving the pandemic, and I think more research on that is needed. But of course, there are lots of questions. The role of children, the understanding of the immunity. I mean, there are lots of things. So it's not a clear cut. No.
Gianpaolo, did you have a question?
Scalia Tomba, come out.
Well, if not, we've kept you rather long, Daniela, so I think we should.
Sorry, I kept you rather long. I have to say that I'm very tired. So when I'm tired, I go slowly, and it took too long for me to.
Anyway, but that wasn't come to you, but I think we had some good questions, and so just say thank you very much, and we will conclude the proceedings. And as I said to the other speakers today, we hope you will find time to keep involved in the program, and we will try and make sure you have the information. So if you have any spare time, you can get involved a bit.
Okay.
So thank you very much.
You're welcome. Thank you for listening. Bye.
Bye-bye.
Thank you.
Bye.